Okay, so now let's see the 3 lines lemma. Okay, so let f be a continuous function bounded, defined on S set equals to x plus iy 0 1. So the function is going to be a complex function, and it will be defined uh, on the complex numbers that its real part is between 0 and 1. And we will say that f is analytic in the interior of S. Okay, so suppose that for each y real number we have that absolute value f iy is less than equal m naught, and the absolute value of f1 plus iy is less than equal than m1. Then um, for any set equals x plus iy in S, we will have the absolute value of f of x plus iy is less than equal than m naught 1 minus x and 1 x. Okay, and in other words we can say that if we define kx as the supremum of absolute value of x plus iy, y real number, this is for x in 0 1 close interval, then we can say that um, if we have the function phi x equals to log kx, then this function is convex. And okay, so you can see that if we apply log, we will have here uh, a constant multiplied by 1 minus x, and a constant plus a constant multiplied by x. Okay, so let's prove this. We can assume that m naught m1 are positive, and moreover we can, if we consider another function mz over m naught 1 minus z m1 z. So if we consider now this function, then the proof can be reduced to the case where m naught is equal to 1 and m1 is equal to 1. Okay, so we will have now that absolute value of f iy less than equal to 1, and absolute value of 1 plus y less than equal to 1 for any y real. Okay, and now we want to show that f set absolute value is less than equal to 1 for any set in S. So let's suppose that if the limit when absolute value of y goes to infinity of fx plus iy is equal to 0 uniformly on x, the real part is between 0 and 1. So in this case we can say that there exists y0 positive such that absolute value of x plus iy is less than or equal to 1 for absolute value of y more than y naught, and it will be that f of z absolute value is less than or equal to 1 in the boundary of the rectangle iy0 1 plus iy0 minus iy0 and 1 minus iy0, and we will be using here the maximum principle that guarantees that we will have a maximum at the boundary. So then we will have that if we suppose that this limit, then we have that in the boundary of this y naught or y0 that we have because of this limit goes to 0, then we will have that the absolute value of f is less than or equal to 1 in the boundary of this rectangle, and using the maximum principle we get that at the boundary of the rectangle we have the maximum, but also the maximum principle guarantees that the same estimate is in the interior of the rectangle. This will also happen in the interior of the rectangle. So we knew that the limit when y, absolute value of y, goes to infinity equals 0, then we establish a y naught where we say that absolute value of y was greater than equal than y naught, and then by maximum principle we establish that we will have in the boundary of the rectangle we must have a that the absolute value of fz is less than or equal to 1, and the maximum principle guarantees the same estimate in the interior of the rectangle. Okay, so this will be when we suppose that the limit of, we will supposing that the limit of f of x plus iy is equal to 0 when absolute value of y goes to infinity. This is uniformly in when the real part is between 0 and 1. Okay, so in a more general case, we consider the function fn z equal to f of z e z squared minus 1 over n, and n is a positive integer. Okay, so then we take absolute value of f of n z. This will be equal to, well, absolute value of f of x plus iy, multiply this by e minus y squared over n, multiplied by e x squared minus 1 over n, and this will be less than equal than the absolute value of f of x plus iy, e minus y squared over n. Okay, and this will go to 0 in the limit when absolute value of y goes to infinity. Okay, and it will be uniformly, as we say, always between between, or the real part, between 0 and 1. Okay, and this will be with with hypothesis for f of n. This is to say that f of n of high y absolute value is less than or equal than 1, and absolute value of f of n of 1 plus high y is less than or equal than 1. Okay, so the previous argument will prove that f of n of z is less than or equal than 1, okay, for any n positive integer. Okay, so then if we make that n goes to infinity, we will obtain this result for the general case, proving the 3-line lemma. Okay,